Welcome to today's lesson, which is lesson 5 of topic 5, increasing and decreasing functions. And these are the definitions of an increasing function and a decreasing function. Let me highlight those two words, increasing and decreasing. Okay, but let's first talk intuitively about these two definitions. It's very simple to understand. For example, suppose that I'm going to give you a function, or more specifically the graph of a function, and let's suppose that such graph does something like this. There you go, more or less. Okay, then we can see that we can part the graph into these sections, guys. For example, I can make a partition right here, and then over here, more or less, and then um, from here to infinity. So we have like three sections basically, from minus infinity to this part, and then from this part to this part, and then from this part to plus infinity. And we can realize something right away. You know, in this part, you can actually think that this is like a roller coaster, okay? And from minus infinity to this point, which I can label, let's label it A, and this let's label B. You can see that if you were displacing from left to right in the x-axis, the function is increasing, okay? And if this was a roller coaster, you can see that basically the roller coaster is going up, okay? It's going uphill. And then from A to B, when you move from left to right in the x-axis, then the function is decreasing, okay? It's being less and less and less, or the roller coaster is going downhill, like so. And then once again, from B to plus infinity, we can see that the roller coaster is one more time going uphill, or the function is increasing. And that's all, intuitively speaking and conceptually speaking, that's all that these words mean, increasing and decreasing. We say that in the interval from minus infinity to A, the function is increasing, okay? And then from the interval from A to B, the function is decreasing, and from B to plus infinity, we have that the function is increasing one more time. And this kind of thing can change many times over. For example, I can create another function that does something like this, okay? And I can spot these three, one, two, three, four parts, okay? Let's call them A, B, C, and D. And I can see that the function is increasing from minus infinity to A. The function is increasing. And then from A to B, the function is decreasing. From B to C, the function is increasing one more time. And then finally from C to D, the function is decreasing. And now from D to plus infinity, the function is increasing one more time. So you see how it works. It's basically going uphill or going downhill when we move specifically from left to right in the x-axis. Okay, so that's all it means. And these are the formal definitions, these two definitions. Let me erase this second diagram. And let's talk about the definitions very quickly. Number one says a function f, let's suppose this is function f, is said to be increasing over the interval a comma b if for all x1 and x2 in the interval, in such interval ab, we have that if x1 is less than x2, then f of x2 is greater than f of x1. I made a mistake here. There you have it. Actually, we can put it in this way. I think this sounds much better. If x2 is greater than x1, then f of x2 is greater than f of x1. Yeah, I think that sounds better. And what does this mean? It means the following. For example, if you choose an increasing interval from here, for example, this one, what you can find is this. If you choose any 2 points in here over this interval, and you label them x1 and x2 or whatever other thing, it doesn't matter, and then you locate their corresponding values of the function, which would be obtained in this way. This is f of x1, and if this is x2, then we trace this perpendicular to the x-axis, and then this other perpendicular to the y-axis, so that we can find f of x2. So basically what we can see is the following. If x2 is greater than x1, which in fact they are, okay, then f of x2 is greater than f of x1. You see? And that's what the definition of increasing means. That if you take two numbers in this interval, okay, two numbers like so, and if one is greater than the other, like so, then the function evaluated in the greatest number will be also greater than the function evaluated in the lesser number. That's how it works. So as long as your function satisfies this definition, we can say that it's increasing over this interval. And the same works for the other definition, for decreasing. Let me one more time. Let me draw this diagram more or less. Just, a diagram doesn't have to be very clear, or a sketch. That's what I mean. And one more time, for example, we know that the function is decreasing. I mean, conceptually, we know that it is decreasing from A to B. Okay, in this section, the function is going downhill. So let's see if it satisfies this definition. What does it say? A function f is said to be decreasing over the interval AB if for all x1 and x2 in such interval AB, we have that if x1 is less than x2, then f of x1 is greater than f of x2. Pay a lot of attention, guys, to these two statements because they are different, okay? Just, they are different only in this sign, okay? In this greater or lesser sign. But that makes the whole thing different. For example, if I choose two numbers here and I label them x1 and x2 or whatever I want, and then I locate the values of the function x1, therefore this is f of x1, this is x2, therefore this is f of x2. We can clearly see that f of x1 is greater than f of x2. Okay, so in this case we have the following. If if x1 is less than x2, which in fact that's the case, x1 is less than x2, then f of x1 is greater than f of x2. You see, f of x1 is greater than f of x2. So this is what it means to be a decreasing function over such interval, over the interval a and a to b. If you pick any two numbers in this place in such a way that one is greater than the other, then the function evaluated in the greatest number has to be less than the function evaluated in the lesser number. You see, it's very simple to understand. The concept is more simple to understand than the definition, but once you understand the concept, the definition comes very natural. Okay, fine. Now, what else? What else can we say about these functions? How do we know, for example, if I give you a function, any function whatsoever, for example, this function, okay? How do we know over what intervals this function will be increasing and over what intervals this function will be decreasing? Well, we can help ourselves with calculus. Okay, we can know with calculus, more specifically with the derivative of this function. Let me tell you why. This is another application of the derivative, knowing in what intervals any function whatsoever, any function will be increasing or decreasing. And let me explain to you why first conceptually, one more time, just conceptually. For example, if we have this function f, you can agree that the function is increasing over this interval from infinity to a, and then it's decreasing from a to b, and then it's again increasing. Now, remember that the derivative helps us find one thing, and that one thing is, at this point, finding the slope of the tangent uh, to the graph of this function at any point I want. And you have to understand this, guys. When, for example, if you go over deciding these 3 points, for example, one point over the increasing period, over the increasing interval, another point over the decreasing interval, and another point over, one more time, the increasing interval. If you calculate the slope, or basically if you draw the slope to the tangent to the graph of f at this point, you will see that the tangent has a positive slope. Remember that lines that look like so, like this, all of these have positive slopes, and lines that look in these directions, okay, tilted in this direction, have negative slopes. I hope you remember this. And I'm taking into reference, of course, the normal Cartesian plane, like in this direction. Okay, all the lines that look like this with these inclinations in this direction, all of these have positive slopes, and all of these have negative slopes. Okay, so basically what I was telling you is this: in any point which is on an increasing interval, when you graph the tangent, okay, to the graph at that precise point, you will see that it has a positive slope. And what happens when you draw the tangent, to the graph of the function at a point which belongs in a decreasing interval? Well, let's see. It's right here, and as you can see, the tangent has a negative slope. You see, and one more time, this other point belongs in an increasing interval, and the slope is one more time positive, the slope of the tangent. And that happens all the time, guys, okay? The slopes, let me write that down. The slopes of the tangents to f over increasing intervals are positive, and over decreasing intervals are negative. So we know about that. Okay, and these other things, guys, in here, look, I'm gonna erase these three tangents. Oops, this, and we should be aware of these other things, okay? These summits and these valleys, okay? This one right here, this point, and this other point. We can call this a valley, and this an apex or a summit, something like that. This is not the precise name. You're gonna get to know the precise name a little later. And you can see that basically the function changes behavior once it goes past these 2 points. Okay, after this point, I'm sorry, before this point, the function was increasing, and after this point, the function was decreasing, 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 and then after this point, it goes up again, increasing. So these are like inflection points. Okay, And in fact, those are the proper names. Inflection points, because that's inflection points, because that's where the function changes behavior. Okay, so basically, and what happens at those 2 points with regards to the tangent? If we draw the tangent at those points, okay, what can you observe? What is the slope of these two tangents, guys? What is the slope of a horizontal line? The slope of these things is 0, right? In both of them. So basically, we can see that the changes in the direction of the function, whether from increasing to decreasing or from decreasing to increasing, happen always at these inflection points, which always have slopes of 0 to their tangents. Okay? Okay, guys, so now that we understand the basic idea behind increasing and decreasing functions, I'm going to show you how to use calculus, and more specifically the derivative, in order to know analytically in what intervals a function is either increasing or decreasing. Okay, so we're going to do that right now. Okay, we're gonna explore all of these functions: this quadratic function, this cubic function, this function square root, and another cubic function, this one. Okay, so let's start with an easy example. So we have this function, right? And like I told you before, and graphically, it's very easy to see in what intervals this function is decreasing, okay, which would be all the numbers from minus infinity to 1, okay? From minus infinity to 1, the function is decreasing, and from this number 1 up until plus infinity, this function will be increasing. So it's very simple to see that with a graph. But what if I don't give you the graph? Suppose that you don't have the graph right here. What would be the approach to follow? Well, the approach to follow is this. What you want to find is basically finding those numbers along the x-axis, okay, in this case 1, for which you have a tangent to the function, okay, which has a slope equal to 0, okay, equal to 0. Why? Because of what I explained before. Because for those numbers, for those numbers of x, okay, these are called turning points. And basically, at this point happens a change in behavior from decreasing to increasing or vice versa. Okay, so we're gonna find all these numbers that are turning points, that are possible turning points. And for those turning points, the slope of the tangent has to be 0. You see? So what do we do? What we do is the following. Take your function, get the derivative. Okay, this is the derivative of my function. And what this derivative does for me, at least one of the things that it can do for me, is calculate the slope of the tangent at any point x that I place right there. Okay, that's basically what this gives me. So for example, if I want to calculate the slope of this function at this point 2, let me erase this thing for the moment. If I want to calculate the slope of this tangent that goes through 2 right there, all I need to do is put the number 2 there, calculate, and that's it. The derivative is going to tell me what's going to be the slope of this tangent. That's how it works. Okay, so I want to know for what I want to reverse the question, so to speak. I want to find for what values along the x-axis, for what values do I get that the slope of the tangent at that precise value is actually 0. That's what I want. So what you do is this. You take the derivative, which is this, 2x minus 2, and you're going to make it equal to 0. You're asking this question. For what numbers x, do I get that the slope of the tangent, which is the derivative, all of this, is equal to 0? And basically, you proceed to answer such question, which means solving this equation. We're going to get 1. Okay? So basically, mathematics is answering you. For x equals 1, you get that the slope of the tangent to f is 0. This is what it means, okay? This is it. We're putting in a phrase all that we have discovered, which is in fact true, right? Look, for x equals 1, right there, we get that the slope of the tangent is 0, and we get this turning point. So basically, we say that this point, x equals 1, in this case, comma 1, is a turning point. And what happens right there? My function goes from decreasing behavior to an increasing behavior. Now, how do I know? For example, remember, we're supposing that we don't know the graph yet. I'm just putting this as a reference. But how do I know whether from minus infinity to 1 is decreasing and from 1 to infinity is increasing, and not the other way around? If you don't have the graph, you don't know. So what can you do? Okay, what you have to do is this, guys. All you have to do is evaluate the derivative one more time, which is this. You're going to evaluate the derivative if in any number before and after this certain point, before and after 1, right? This point. For example, we can evaluate in minus 1 right here. Let's evaluate the derivative in minus 1. Evaluate f prime in x equals minus 1. So let's do it. F prime of minus 1 will be equal to 2 times minus 1 minus 2. And what do we get? Minus 2 minus 2, we get minus 4. Okay, and what does that tell me? That tells me that the slope of this at this precise point is negative, and that means, well, that's not a very good straight line. And that means, guys, that my function over this interval from minus infinity to 1 is decreasing over this region. Okay, so the function is decreasing from minus infinity to 1. All right, and now all I do next is do the same for the other part of my interval, okay, which is from 1 to infinity. I'm going to evaluate in any point over here to the right of 1. For example, for 3, we can evaluate the derivative for 3 to get the slope in here. Let's do it. Let's do it over here. Let's evaluate f prime in x equals 3. And what do we get? We get f prime of 3 is equal to 2 times 3 minus 2, which is going to be 4. Okay, so it's basically positive. That's all we care about, the sign. We don't care about the number, really. We care about the sign. So the sign being positive tells me that the function is increasing in that interval from 1 to infinity. So we get increasing. It's increasing from 1 to infinity. Okay, and that's how it works, guys. Basically, you get the turning points. You get the possible turning points. Okay, in this case, it's just 1. There you have it. And then this, let me erase everything one more time. There you have it. This is your turning point. And basically what you have to do is evaluate the derivative to the right, I'm sorry, to the left and to the right of such turning point. And according to the sign of the derivative in such evaluation, for example, if you get that in this zone, you get that f prime is negative, okay, that means that the function is decreasing. And if in that zone you get that the derivative is positive, that means that the function is increasing, okay. And the other way around, if we would have gotten this instead, like this, no, I'm sorry, I wrote the same thing. If we would have gotten this, then that would have meant that over this region from minus infinity to 1, the function would have been increasing, and in this zone it would have been decreasing. You see, so that's how it works. That's how it works. And you don't need the graph for doing this type of analysis. Okay, let's do another one. I want you to write down this function, please, because we're gonna do it without making any reference to the graph. We're gonna do it in the blackboard. So I'm also writing it down. And try not to look at the graph so that you're not biased. So that's the function, okay? This is the function. Okay, and what do we need to know? We want to know in what intervals is this function increasing or decreasing. So here it goes. Here is the function. 1/3 of x to the cube minus 1/2 of x squared minus 2x plus 2. And now we're not going to make any reference to the graph, okay? At the end, we're going to check with the graph. But in the meantime, it's purely analysis, which is actually it's the way in which mathematics must be done, okay? Because you don't always have this technology at your hands, right? Graphing calculators and all these things. What you always have though is pencil and paper. Okay, so let's see. What do we need to know? In what intervals is f increasing and in what intervals it is decreasing. Okay, so what do we know? What do we do? Number one, get the derivative of the function, get f prime. So let's do it. F prime of x is equal to, I'm gonna go do it directly. It's very simple. Okay, yes, this is the one. Make sure, if you want to pause the video, do it, get the derivative, and you should get this. Okay, fine. So this is the derivative. And remember, the derivative tells us the slope of the tangent to the function f at any point we want, at any point x. Okay. So number 2, what are the turning points? What are the turning points? Okay. Well, the turning points when a function goes from like increasing to decreasing, remember this is the turning point, or the other way around, when it goes from decreasing to increasing, those points happen when the slope is 0. So basically when the derivative is 0, because the derivative tells us the slope. So that's all we need to know. We need to know, okay, if this is my derivative, if all of this is my derivative, then what values of x will make the derivative equal to 0? And that's the question I'm asking. Okay, you can see this as a question. You're asking mathematics this question. Okay, and the proper way to solve it is solving the equation. We can actually factorize this trinomial, and we can get these two solutions, x equals 1 and x equals minus 1. So these are your two solutions for this equation. Okay, so these are my possible turning points. You know, you're gonna start listening, or you're gonna start hearing that I call this the possible turning points. I'm adding this adjective, possible turning points. And you're gonna know in the last example that I'm gonna give you today, you're gonna know why these are not necessarily turning points. These are not necessarily. They can be possible points, but not necessarily. Okay, so x equals 2 and x equals minus 1 are possible turning points. Let me continue over here. And now all I need to do is this. Basically, these turning points divide my my domain, which is the x-axis. Okay, remember, we're not gonna draw the graph. I'm just sketching right here. These 2 points divide my x-axis into 3 parts. Okay, x equals minus 1 is over here more or less, and x equals 2 is over here more or less. Minus 1 and 2. So basically, what I should expect is this. Okay, um, I expect to see my domain divided into three zones, which is from minus infinity to minus 1. Okay, let's call that those things intervals. Intervals. We have 3 intervals. Interval 1, we have from minus infinity to minus 1. The second interval is from minus 1 up until 2. And the third interval is from 2 to infinity. You see? So maybe our graph will behave in this way. Maybe it's gonna look like this. Um, okay, it could look like this. You see, from minus infinity to minus 1, it's decreasing, and then from minus 1 to 2, it's gonna be increasing, and then from 2 to plus infinity, we get decreasing behavior again. Now, it could look like this, but it also could look like this. Like increasing, and then at this point, it goes decreasing, and then at this point, at this turning point, we get increasing behavior again. So how do we know which one is it? Okay, how do we know in what way my function is behaving over each of these 1, 2, and 3 intervals? What we do is we take any number. It doesn't matter with what number. Choose an easy one, okay, an easy target. For example, pick any number to the left of this point. For example, minus 2. I'm going to choose minus 2. I'm always going to choose integers, okay? And then over this region, I'm going to choose 0. And over this zone or interval, I'm going to get 3. Just integers for simplicity. And what I need to do is evaluate the derivative in each of these 3 points and look at the sign of the derivative. What is my derivative? It's this one. Okay, so in this interval, in my first interval, I'm going to evaluate my derivative in my chosen number, which is minus 2. So f prime of minus 2, that's going to be equal to minus 2 to the square minus 2 minus 2. And this is going to be 4 plus 2, 6 minus, this is going to be 4, guys. Make sure, 4 plus, no, it's going to be 6, right? We get 4 plus 4, 8, minus 2, 6. Yeah, we get 6. And remember, the number itself is not important. What we care about is the sign. It's positive, okay? It's positive. That's all I care about. I don't care about the 6. I care about the sign. It's positive. And that alone tells me right away that my function is increasing over the interval from minus infinity to minus 1. So let me put it in yellow. Over here we get increasing behavior. We know that for a fact. Now let's do the same thing for this other interval from minus 2 to 2. Let's evaluate in my chosen value of 0. Remember, these values are completely random. You can choose any number as long as it's inside the interval. So let's evaluate f prime in 0. We get 0 to the square minus 0 minus 2. So basically we get minus 2. And remember, what matters is the sign. This is negative. Okay, so that lets me know that the behavior of my function over the interval from minus 1 to 2 is decreasing. Okay, so it goes like this. It goes increasing, and at this turning point, which is minus 1, it goes decreasing, and probably we expect that at this turning point of 2, it goes back increasing again. But we have to make sure. So over this other interval, my last interval, I chose the number 3 for the evaluation. F prime of 3, we get 3 to the square minus 3 minus 2, we get 9. 9 minus 3 minus 2, we get 4 again. And again, this is positive, so that tells me that the behavior of the function is increasing over this last interval. So that's it, guys. We have completed the task. We have completed and solved completely the task. The task was this: in what intervals is f increasing and decreasing? And we have found that over the interval from minus 1 to minus 1, from minus infinity to minus 1, my function is increasing. Okay, now I can erase these numbers, these red numbers. I don't need them anymore. And so my function will look, roughly speaking, it's gonna look like this. Roughly speaking, it's gonna look increasing, turning point right here. And then from minus 1 to 2, which is in this interval, I'm gonna get decreasing behavior. So I'm gonna get this. And then at this point, at this turning point, I'm gonna get one more time increasing behavior. Okay, now I don't know, you gotta make sure of this, guys. I don't know whether, for example, I don't want to confuse you here. For example, I could have also drawn this instead of this one. I could have drawn, for example, this. Okay, and this other red function also complies with these 3 facts, right? It goes increasing, decreasing, and increasing again. So which one is it? Is it the yellow one? Is it the red one? Is it other type? You don't know. You need more information. All you know at this point, all you know about the function f, about the graph of this function, is that is the behavior with regards to its increasing or decreasing behavior over these intervals. But in order to know more information about the graph, in order to be able to actually draw it, you need more info. Okay, you need, like, for example, the zeros, okay, which are the numbers at which it crosses the x-axis, and maybe other things. But at least you know the behavior over these 3 intervals, whether it's increasing or decreasing. And let's check. Let's compare it with the actual graph. There you have it. You see? Look, minus 1, you get increasing behavior, up until -1, and then from -1 to, I think I, give me a moment because -1, no, yeah, I was getting confused. From -infinity to -1, you get increasing behavior, and then from -1 to 2, you get, look, you get decreasing behavior up until 2, and from 2 onwards, you get one more time increasing behavior. You see, that's all you know so far. You need more information, of course, in order to graph the function, but that's enough to give you a rough idea of the function. So that confirms our work that we did over here, and that's how you do it, guys. Let's work out another example. This one, f of x equals the square root of x. Okay, just take a brief look at the graph. See how it's always increasing, always increasing. Look, it's always increasing. It never goes down. So how am I gonna see that when I study the function analytically? What's it gonna look? Let's see. We have f of x equals the square root of x, and I'm gonna follow the same idea as I showed you a moment ago. Okay, number one, get the derivative, get f prime. So f of x can be written in this way, right? In order to perform the derivative. And so f prime of x is gonna be 1/2 of x to the -1/2. There it is. And I can put it, if I don't want to use negative exponents, I can write it in this way, 1/2 times x to the 1/2, and f prime of x equals 1/2 times 1 over the square root of x, or finally, in a much more aesthetic way, 1 over 2 times the square root of x. So this is my derivative, guys. This is my derivative. Either way, I mean, this, and this are all the same, but I think this one looks the better. Okay, so I got the derivative. Now what? Okay, ask the question. What are the turning points? What are the possible turning points? The possible turning points of f. Okay, how do I answer that question? Okay, what I need to do is make the derivative equal to 0. Okay, this is my derivative. Make it equal to 0 and try to solve this equation. Try to solve this equation. When you try to solve it, guys, you're gonna find that you're gonna find the following. You can multiply both sides times this denominator, and you're gonna get 1 equals 0 times this, and then 1 equals 0. You see? So basically you reached a contradiction. You just reached a contradiction. And what this is basically telling you is that there is no such number x. There is no number x such that 1 over 2 times the square root of x is going to be equal to 0. Okay? Never. That's not going to happen. So basically, the mathematics is telling you there is no turning point, or there are no turning points. Okay? There are no turning points. And that's it, guys. There are no turning points. So then what that means is that my function is either always increasing or always decreasing. Okay, it only has one type of behavior. It doesn't have turning points. It doesn't go like increasing and then turning point, decreasing. No, it never happens in this case, or the other way around, decreasing and then reaching a turning point and then increasing again. No, this is the type of function that always has one type of behavior, either always increasing, okay, like for example a linear function in this way, or always decreasing. You see, always, and there are such functions. Okay, those are pretty normal functions. Okay, and so which one is it? Which one is this function? Is it always increasing or is it always decreasing? How do we know? Same idea. Evaluate the derivative. Evaluate the derivative in any point you want. In any point, it doesn't matter. So number 3, evaluate the derivative in any point. Well, in any valid point, obviously, in any valid point. Because if this is my derivative, I cannot evaluate this thing in negative values of x, right? So you're gonna evaluate in any valid point. Valid point. For example, in 1. So let's evaluate f prime of 1. That's gonna be 1 over 2 times the square root of 1, which is 1/2. There you go. So it's positive. The sign of this evaluation is positive, and what that tells me is that my function is always increasing. This is my conclusion. I'm done. My function is always increasing. Why? Because when I looked for possible turning points, I found that there were not any, because I could not solve this equation, the derivative equal to 0. I could not solve it, and that means there are no turning points. It's just the mathematical way of knowing that there are no turning points. So my function is either always increasing or always decreasing. How do I know? I evaluate the derivative in any point. I don't care what point, as long as it's valid. And if the derivative is positive, your function is increasing. And if this would have been negative, then your function is always decreasing. And like I already showed you the graph, right? You see, it's always increasing, always increasing. When you draw the slope, when you draw the tangent to this function anywhere, it doesn't matter. You always get that the slopes are positive, always positive. You see, positive, 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 positive. This function is always increasing. All right, perfect. And now let's go over the last function. Okay, again, I'm not gonna show you the graph because I don't want you to be biased. And let's see, the last function we're gonna investigate is the function x to the cube. Very simple function. Let's do the same thing. Number 1, get f prime. Quickly, we get f prime of x equals 3x squared. Number 2, what are the turning points? Try to find them. There may be, there may not be turning points. How do we know? Well, get the derivative, which is 3x squared, make it equal to 0, and try to answer this question mathematically. Okay, so it's a very simple equation to solve. We get that x equals 0. Okay, that's the only solution basically. Okay, so maybe this is a possible turning point, and there is that word again, possible. It's a possible turning point. That doesn't mean that it will be. It's just a possibility. How do I know whether it's a turning point or not? Well, we have my Cartesian plane, and at 0, right at this point, I'm gonna do it again in blue. I might expect that if this is a turning point, then the behavior should go from either decreasing towards increasing, or the other way around, from increasing to decreasing. You see, that's what I should observe if this is in fact a turning point. But is it? Is it really? Let's see. How do I find out? Okay, one more time. My turning point, which is 0, well, my possible turning point, divides the x-axis, in this case, into two intervals. Number 1 from minus infinity to 0, and the second interval from 0 to plus infinity. There you go. And all I need to know now, in order to see what type of behavior is my function showing to the left or to the right of this turning point, of this possible turning point, all I need to do is evaluate the derivative. I get the derivative, I evaluate it in any number, let's say minus 1 and in 1, and let's see what get out of those evaluations. Let's evaluate the derivative of minus 1. So it's going to be 3 times minus 1 to the square. So I get 3. And all I care about is the sign. It's positive. So that tells me that over this interval, my function is increasing. Increasing. And I do the same for the other interval from 0 to infinity. So one more time, I evaluate in my chosen value. I chose 1. So I get 3 times 1 to the square, which is also 3. And it's also positive. This is what I care about, the signs. And that tells me, the conclusion is that over the interval from 0 to plus infinity, my function is always increasing. So how come? How come? How is this possible? Before this apparently turning point, the function is increasing, and once it goes past this point, the function is also increasing. You see, so it's not changing behavior. How can that be? Okay, so that's why I told you guys that this is a just a possible turning point. In this case, what we found is that in fact 0 x equals 0 is not a turning point. Not a turning point. And how does that look visually or graphically? Let's see. Look at this. There you have it. Look at what's happening to this function x to the cube when we are at 0. When we are at 0, guys, what we can observe is that well, let me erase everything already. What we can see is that the tangents, for example, look at this tangent. It's positive, so it's increasing. My function is increasing. It's also positive here. But when it reaches this 0, that tangent, guys, sort of looks like this. Okay, it's completely flat, completely horizontal, and that's why we also get that value of 0, because at that point the tangent is also horizontal, and then once it goes beyond 0, we also get that the tangent gets a positive slope. So it's always positive, you see, positive, 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 0, 0, but not a turning point, and then positive, positive, positive. So it's increasing, 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 and then at this moment it stops increasing, so to speak. You know, it comes to a halt, to a pause, but then it goes again increasing my function. You see, it's another type of behavior. The function is increasing, increasing very quickly first, and then slowly, 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 slowly. It barely moves at this point, you know, and then it halts at this point. It stops increasing, and after 0, we get also increasing, 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 and then quicker, quicker, and quicker, and quicker. So you see, you gotta make sure that you don't fall into that trap, because not always Not always when you um, I everything I erased already. Well, never mind. Not always when you find these possible turning points. Okay, the possible turning points. Not always they in fact are turning points. Okay, so you gotta make sure about that. And I believe that's the whole lesson, guys. Pretty long. And now let's go down to the exercises. If you have questions, you can ask me. So there we go.